Good afternoon. My name is Mark Esteri. I'm talking about my project about next generation coconut carbon processing. My project focuses on the design of a next generation coconut carbon processing system that converts coconut shell waste into activated carbon for water filtration. Activated carbon is a critical material used in water purification, air filtration, and industrial absorption. However, traditional activated carbon production is energy intensive, fossil fuel dependent, and often geographically concentrated, which limits scalability and sustainability. The system I'm proposing integrates with biochar or coconut processing facilities and upgrades coconut shell waste into high surface area activated carbon through a controlled thermal and activation process. The main stakeholders include biochar facilities, water filtration manufacturers, environmental regulators, and investors interested in sustainable materials. The objectives are to reduce energy consumption by at least 20% compared to conventional activation plants and improve absorption performance by about 40% compared to untreated biochar. Key constraints include high temperatures required for activation, complex gas and steam control, and regulatory emission requirements. Using system as engineering methods, the project focuses on translating these needs into a clear functional requirements, architecture design, and simulation validation. From these system needs, I developed a structured set of functional and performance requirements for the plant. First, the system must handle variable feedstock conditions, since coconut shell waste can vary significantly in moisture and composition. For example, the system must process feedstock with 10 to 35% moisture content and tolerate up to 5% fiber husk contamination without causing reactor plugging. Next, the carbonization stage must occur in an enclosed reactor system. This prevents soil or silica contamination that occurs in traditional open burning methods and ensures consistent char quality. The reactor must operate at temperatures above 800 degrees Celsius while maintaining a controlled air to fuel ratio and capturing at least 95% of off gas for energy recovery. Another key requirement is energy integration. Producer gas generated during carbonization should be reused as fuel so the system can meet most of its thermal demand internally, with external fuel limited to 30% of total energy reused. The system must also include steam activation and temperatures up to roughly 1100 degrees Celsius, producing activated carbon with higher hardness and micropore structure suitable for filtration. Finally, additional requirements address the emission controls, plant safety, operator usability, and packaging, ensuring the product can be cooled, sized, and packaged with minimal dust loss and accurate bag filling. Together, these requirements define the technical performance and operational boundaries of the system. Using these requirements, I developed a functional architecture of the system. The system begins with feedstock processing, where coconut shells from food production waste are cleaned, sized, and prepared for processing. The shells then enter carbonization reactor, where controlled heating converts biomass char while generating producer gas. The producer gas is routed through a gas handling and cleaning subsystem, which removes particulates and enables the gas to be reused for combusting or heat recovery. Next, the char enters activation stage, where high temperature steam activation develops the microporous structure that gives activated carbon its absorption capacity. After activation, the material moves through cooling, screening, and packaging functions, so it can be delivered as commercial granular activated carbon. The functional architecture shows how the system flows from waste feedstock to a finished filtration media, while integrating the energy recovery and environmental controls throughout the process. To reduce development risk before building a full system, I developed a simple model and simulation framework. The goal of this model is to evaluate whether coconut processing waste can reliably supply enough activated carbon to support water filter production. The simulation converts coconut shell input into carbon output, activated carbon output, using several modeled variables, including shell supply rate, moisture content, carbonization yield, activation burn-off rate, and plant uptime. I then tested several operational scenarios. This include normal feedstock supply, higher moisture feedstock, reduced shell availability, and increased filter demand. And by modeling these scenarios, we can estimate the daily activated carbon production capacity and determine whether the plant can meet internal demand. This approach helps identify minimum feedstock requirements, optimal production scheduling, and potential bottlenecks before investing in physical infrastructure. Overall, the modeling component reduces uncertainty and supports data-driven design decisions during an early system development.